This video covers Part 1 of Section 7.5, the symmetric and alternating groups. In this section, we want to examine the symmetric groups S sub n in more detail. We start by introducing a simplified notation for permutations. To illustrate the notation, we'll use an example. So consider the permutation of S7 shown. So in this permutation, 1 maps to 5, 5 maps to 3, 3 maps to 4, 4 maps to 7, and 7 maps back to 1. Also, 2 maps to itself, and 6 maps to itself. We can illustrate the action of the permutation by the following diagram. So we have 1 maps to 5, 5 maps to 3, 3 maps to 4, 4 maps to 7, and 7 maps back to 1. And then 2 maps to itself, and 6 maps to itself. We can then represent the permutation with the notation shown. So we have 1, 5, 3, 4, 7 enclosed in parentheses, and then 2 enclosed in parentheses by itself, and 6 enclosed in parentheses by itself. This is an example of what is called cycle notation. And here's the formal definition. So let A1, A2, A3 up to A sub k with k greater than or equal to 1 be distinct elements of the set 1, 2, 3 up to n. Then parentheses A1, A2, A3 down to A sub k, close parentheses, denotes the permutation in S sub n that maps A1 to A2, A2 to A3, down to A sub k minus 1 to A sub k, and then A sub k back to A1, and every other element of 1, 2, 3 up to n which doesn't appear in the parentheses is mapped to itself. And we can visualize the permutation by the following diagram. So A1 maps to A2, A2 to A3, all the way down to A sub k minus 1 maps to A sub k, and then A sub k maps back to A sub 1. Now the permutation A1, A2, A3 down to A sub k is called a cycle of length k, or a k-cycle. For an example, let's write out the permutations 1, 3, 5, 4, 1, 2, 3, 4, 5, 6, and 1 for n equals 6. So we're in the permutation group S sub 6. To write out these permutations, what we can do is consider the image of each element of the set 1, 2, 3, 4, 5, 6 in turn. So we'll start with 1, 3, 5, 4, and we'll use the two-row notation for the permutation. So we'll start with the top row is 1, 2, 3, 4, 5, 6. And what we want to do is we want to see what each of the images of the elements 1, 2, 3, 4, 5, 6 is in our cycle. So in our cycle, 1 maps to 3. So we can indicate that by putting the 3 below the 1. 2 maps to itself, since it doesn't appear in the cycle. 3 maps to 5, so we'll put a 5 under the 3. 4 maps to 1, so we'll put a 1 under the 4. 5 maps to 4, we'll put a 4 in there. And then 6 doesn't appear in the cycle, so 6 maps to itself. So there's the permutation indicated by that cycle 1, 3, 5, 4. For our next example, we have the cycle 1, 2, 3, 4, 5, 6. So we'll start off again with the two-row notation with 1, 2, 3, 4, 5, 6 in the top row. And again, we want to consider the image of each element in turn. So in our cycle, 1 maps to 2, so we've got a 2 in there. 2 maps to 3, so we'll put a 3 under the 2. 3 maps to 4, we'll put a 4 under the 3. 4 maps to 5, we'll put a 5 under the 4. 5 maps to 6, we'll put a 6 under the 5. And 6 maps back to 1, so we'll put a 1 under the 6. And so there's the cycle 1, 2, 3, 4, 5, 6. Now the permutation 1 just maps 1 to itself and each other element to itself. So 1 will be the permutation 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, and 6 to 6, which equals the identity permutation. Now the 4 cycle 1, 3, 5, 4 maps 1 to 3, 3 to 5, 5 to 4, and 4 to 1. Note that 1354 may also be denoted by 3541 or 5413 or 4135, since each of these also maps 1 to 3, 3 to 5, 5 to 4, and 4 to 1. Now, one drawback to the cycle notation is that it's ambiguous, since, for example, a cycle 1354 could denote a permutation in S5 or S6 or any S sub n with n greater than or equal to 5. This doesn't usually create a problem, since we usually know what group we are working with. Now, we can use the cycle notation to compute products, that is, compositions of two permutations. For our example, let's let sigma be the cycle 1354 and tau be the cycle 23456 in S sub 6. And we want to compute the products, or compositions, sigma tau and tau sigma. So when we write sigma tau, we really mean sigma composed with tau, and when we write tau sigma, we really mean tau composed with sigma. Now, to compute sigma tau, remember, since this is a composition, we apply tau first, since it appears on the right, and sigma second. So let's write out sigma tau is 1354 composed with 23456. And to compute this, we'll go ahead and write out the first row in our two-row form for our permutation. And we'll start by looking at the image of 1 under the product. So in tau, 1 doesn't appear. So that means that tau keeps 1 fixed, but in sigma, 1 maps to 3. So in the product, 1 will map to 3. Next, we'll look at 2. In tau, 2 maps to 3, and in sigma, 3 maps to 5. So that tells us that in the product, 2 maps to 5. Next, let's look at 3. So in tau, 3 maps to 4, and in sigma, 4 maps to 1. So in the product, 3 maps to 1. For 4, in tau, 4 maps to 5, and in sigma, 5 maps to 4. So that means that in the product, 4 will map to 4. In tau, 5 maps to 6, and in sigma, 6 is fixed. So in the product, 5 maps to 6. And then in tau, 6 maps to 2, and in sigma, 2 is fixed. So in the product, 6 maps to 2. And so there's the product sigma tau. And to compute tau sigma, we apply sigma first and then tau. So we'll start off the same way. And then in sigma, 1 maps to 3. In tau, 3 maps to 4. So in the product, 1 maps to 4. In sigma, 2 is fixed. And in tau, 2 maps to 3. So in the product, 2 will map to 3. In sigma, 3 maps to 5. And in tau, 5 maps to 6. So in the product, 3 maps to 6. In sigma, 4 maps to 1, and in tau, 1 is fixed. So in the product, 4 maps to 1. In sigma, 5 maps to 4, and in tau, 4 maps back to 5. So in the product, 5 maps to itself. And in sigma, 6 is fixed. In tau, 6 maps to 2. So in the product, 6 maps to 2. So there's the product tau sigma. Now, one thing to notice is that these two products are not equal to one another, which is typical when you're composing functions. In general, function composition is not commutative. Now, we can compute these products again. Alternatively, we can compute the products in cycle notation. We then want to compute the image of each element as it arises in the cycles. So we'll write out sigma tau again. And instead of using the two-row form, I want to use the cycle notation. And so I'll start with a cycle containing 1. And so I want to look at the image of 1 under the product. So in tau, 1 is fixed, and in sigma, 1 maps to 3. So in the product, 1 will map to 3, and I can indicate that by putting 3 next to 1 in the cycle. Now I want to look at the image of 3. Well, in tau, 3 maps to 4, and in sigma, 4 maps to 1. So in the product, 3 will map to 1, which tells me that I want to close off my cycle. So now the first element that doesn't appear in the cycle so far is 2. So I'm going to open up a new cycle with 2. And then in tau, 2 maps to 3, and in sigma, 3 maps to 5. So in the product, 2 will map to 5. And then I want to look at the image of 5. So in tau, 5 maps to 6, and in sigma, 6 is fixed. So in the product, 5 will map to 6. Now we'll look at the image of 6. In tau, 6 maps to 2, and in sigma, 2 is fixed. So in the product, 6 will map to 2. So I'll close off that cycle. That will give me a cycle which maps 6 to 2. Then now the next element that doesn't appear in a cycle so far is 4. So I'll start a new cycle with 4. And in tau, 4 maps to 5. And in sigma, 5 maps to 4. So that tells me that in the product, 4 will map to itself. And I can indicate that by closing off the cycle. Now that takes care of all of the elements 1, 2, 3, 4, 5, 6. So that will be my product. And we can compute tau sigma in a similar manner. So we'll start with a cycle with 1, and then in sigma, 1 maps to 3, and in tau, 3 maps to 4. So in the product, 1 will map to 4. And then I want to look at the image of 4. Well, in sigma, 4 maps to 1, and then in tau, 1 is fixed. So in the product, 4 will map to 1, so I want to close off this cycle. And I'll start a new cycle. The first element that doesn't appear is 2. And in sigma, 2 is fixed. And in tau, 2 maps to 3. So in the product, 2 will map to 3. Let's look at the image of 3 next. So in sigma, 3 maps to 5. And in tau, 5 maps to 6. So that means in the product, 3 will map to 6. And now in sigma, 6 is fixed. In tau, 6 maps to 2. So that tells me in the product that 6 will map to 2, so I want to close off that cycle, 2, 3, 6. That will give me a cycle where 6 maps to 2. And now the first element that doesn't appear is 5, so I'll start a new cycle with 5. And in sigma, 5 maps to 4, and in tau, 4 maps back to 5. So in the product, 5 will map to itself, and so I'll close off that cycle. And that gives me the image of each element 1, 2, 3, 4, 5, 6. So that will be the product tau sigma. For another example, let's let sigma be the 2 cycle, 1, 4, and tau will be the 4 cycle, 2, 3, 5, 6 in S6. And again, we want to compute the products or compositions, sigma tau and tau sigma. So sigma tau is 1, 4, 2, 3, 5, 6. And I'll set up my 2-row form. And if I look at 1, well, in tau, 1 is fixed, but in sigma, 1 maps to 4. And then if I look at the image of 4, well, in tau, 4 is fixed, and in sigma, 4 maps back to 1. So since 1 and 4 do not appear in tau, then tau leaves both of them fixed, and their images in the product depend only upon sigma. Now let's look at 2, 3, 5, and 6. Well, in tau, 2 maps to 3, and sigma leaves 3 fixed. In tau, 3 maps to 5, and sigma leaves 5 fixed. So in the product, 3 maps to 5. And for 5, tau maps 5 to 6, and sigma leaves it fixed. So 5 maps to 6 in the product. And finally, tau maps 6 to 2, and sigma leaves 2 fixed, so in the product 6 maps to 2. So since 2, 3, 5, and 6 do not appear in sigma, then sigma leaves them fixed. So their images in the product depend only upon tau. This means that the two products, tau sigma and sigma tau, will be equal. Now, two cycles are disjoint provided they have no elements in common. For instance, in the previous example, 1, 4 and 2, 3, 5, 6 are disjoint cycles in S6. In the earlier example, however, the 4 cycle 1, 3, 5, 4 and 5 cycle 2, 3, 4, 5, 6 are not disjoint. They share the elements 3, 4, and 5. So we saw that in the example with the disjoint cycles, the cycles commuted. This did not hold in the example with the non-disjoint cycles. And this is going to be the standard result. So the following theorem shows that in general, disjoint cycles commute. This is Theorem 723, which says if sigma equals a1, a2 down to a sub k, and tau equal b1, b2 down to b sub r are disjoint cycles in S sub n, then sigma tau is equal to tau sigma. Now, not every permutation is a cycle. However, every permutation can be written as a product of disjoint cycles, as shown in the next example. So let's write the permutation shown, so we'll call it sigma, in S sub 9 as a product of disjoint cycles. So we'll start by writing out sigma, and we'll start with a cycle beginning with the element 1. Now the permutation maps 1 to 3, so we'll add 3 to the cycle. Then 3 maps to 4, so we'll add 4 to the cycle. Since 4 maps to 1, this completes the cycle. Now the first element that doesn't belong to the cycle is 2, so we'll start a new cycle with 2. The permutation maps 2 to 9, so add 9 to the cycle. Then 9 maps to 8, 8 maps to 7, and 7 maps back to 2, which completes the cycle. The first element that is not in a cycle yet is 5, so we'll start a new cycle with 5. And 5 maps to itself, so we'll just close off that cycle. And 6 also maps to itself, so this corresponds to a 1 cycle containing 6. And so we have our permutation written as a product of disjoint cycles. Now the procedure used in this example can be generalized to prove the following theorem. This is Theorem 7.24. Every permutation in S sub n is the product of disjoint cycles. Now for any k cycle tau equal a1, a2, a3 down to a sub k, the composition of tau with itself k times will map each element a sub I to itself, so will equal the identity. And this will be the smallest power of tau that equals the identity, so this will equal its order. And this result can be used to prove the following theorem. This is Theorem 725. The order of a permutation tau in S sub n is the least common multiple of the lengths of the disjoint cycles whose product is tau. For an example of this theorem, how we can apply this theorem, let's find the order of the permutation tau equals 1, 2, 3, 4, 5, 6, 7, 8. So tau is the product of disjoint cycles of lengths 2, 3, and 3, so the least common multiple of the lengths of the cycles is 6. Therefore, the order of tau is equal to 6. Now we can verify this directly by computing the powers of tau. So tau is 1, 2, 3, 4, 5, 6, 7, 8. And tau squared, well, the 2 cycle will will equal the identity after we square it, and we'll be left with 3, 4, 5 squared is 3, 5, 4, and 6, 7, 8 squared is 6, 8, 7. Tau cubed will be just the 2 cycle, 1, 2. Tau to the 4th will be 3, 4, 5, 6, 7, 8. Tau to the 5th is 1, 2, 3, 5, 4, 6, 8, 7. And tau to the 6th works out to be the identity permutation. So the first positive integer power that equals the identity other than is 6. So this confirms that the order of tau is equal to 6. And this finishes off part 1 of section 7.5.